Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah. Peace and blessings upon you all. Dear students, in last video we actually started the topic of top-down parsing, and we saw that it's actually the recursive descent, and the recursive descent is of two types, either backtracking or non-backtracking. And the backtracking part we covered actually, and it has a disadvantage of backtracking as well. So we try to remove the backtracking. So we're gonna remove this backtracking in the non-backtracking. And when we say the non-backtracking, we have what's called the predictive parsers. So the predictive parsers basically does not have any backtracking. So we can do without backtracking. But before we can do without backtracking, we have to do what's called as a left factoring. Like we saw here, the left recursiveness, there was left recursiveness, and we removed that, eliminated the left recursive grammars. And here we have what's called the left factoring. Now we'll try to understand all these things, okay? Then later on we will see that predictive parsers can be without the recursion. So non-recursive, what's called the non-recursive predictive parsing, okay? And we will try to use the tables. Okay, we will use the tables, and we use the push down automata, and we'll talk about these things in detail. So in a predictive parser we have which is actually top-down parser. It uses some k tokens. Usually we have k equals to 1 to select a production. We'll see in detail what that means. And it is an efficient because there is no backtracking needed, and it has a linear time to parse, while in case of backtracking, we have an exponential time to parse. Implemented because we have to come back, because there will be wrong productions in backtracking. Then we have to backtrack and come back to the exact production. That will take time. That is exponential. But here we have only one choice, so you have to go. That's why it's a linear time. So it's very fast. So your predictive parser actually can be a recursive descent parser or table-driven parser. In recursive descent, we have each non-terminal parser by a procedure, okay? Then call other procedures to parse sub non-terminals recursively. That's what we call it. It is again a recursive descent. We have procedures which call other procedures and so on, and they call it recursively. And they are typically written by hand. Then table-driven is a much efficient one, which uses the push-down automata. Okay, which is called as actually a table-driven FSA, and it also uses a stack to do recursive calls, and they are typically generated by a tool from a grammar specifications. Okay, so this is written by the hand, this is done by some tool, and we will try to discuss everything. And that's why we say the implementation may be analogous to lexing. Okay. So your predictive parser is actually a recursive descent parser, which actually has a capability to predict which production is to be used to replace the input string. Okay, so it doesn't go for backtracking and try. It doesn't try everything, all productions, and then go backtracking. Okay, it exactly knows which production to use, but it's not a magic how it does these things. So what it has is, it has a look ahead pointer, okay, which actually points to the next input symbol. And to make our parser backtracking free, the predictive parser actually puts some constant on a grammar, so that the grammar should be LLK grammar. This is our constraint. The grammar should be LLK grammar. Then only then it can be predictive parser. It can do the predictions about which production to use. So what is this LLK grammar, and what we need if we don't have LLK grammar? What we need to do is called as a left factoring. Okay, let's try to discuss what is the LLK grammar and what is the left factoring. So this is a precondition. If the grammar is not left factored, that means it's not an LLK grammar. We can't do the predictive parsing. So what we typically say is, for example, we have a goes to alpha or beta. Okay, now the parser should be able to choose between alpha and beta. Okay, now here we have clearly two choices, so we can correctly say, because we have the look ahead pointer which exactly sees what we need, so we can decide on that basis, should we go to the alpha or should we go to the beta. But sometimes the grammar is not so obvious. Okay, so that is why we say that we need the left factoring of a grammar to make it the LLK grammar. Now if we see this grammar where we have E goes to T plus E or T. Okay, now what about this grammar? Look at this grammar. So if we want to go from E, and we know we have some choice where we need to go to the T. Maybe look at is telling us that we need to go to the T from the E. Okay, but there are two choices. Should we go to this T or should we go to this T? Is it? So this is the ambiguity in it. So that's why we say we need what's called the left factoring. Okay, so this is not left factored grammar. So this can't be LLK grammar, which we talk in detail later. So what I'm saying, we need first to do left factoring of this type of grammar, right? So let's say in general that if we have, for example, A goes to alpha beta 1 or alpha beta n, there may be many alpha beta 2, alpha beta 3 and so on, and then there may also be the gamma, which has nothing to do with the alpha. So these beta 1s and beta up to the beta n or many betas, they have a prefix alpha which is common. So that will create a confusion in a compiler, that should we take this as an alpha or this as alpha or this as alpha, because we say predictive parsing, we should have a clear choice that hey, we're gonna do this. And gamma is something which has nothing to do with the alpha, it's something else. Okay, like we said here, T plus E, there may be something like A. Now A has nothing to do with the T, so there is no confusion. So that this A is the gamma, and this T is a prefix, that's my alpha. Okay, that means I have a grammar where I have common prefixes. Then there may be something else after that, suffix can be something else, that's not a problem. But prefix is a problem, because we have to make a choice, should we take this production or should we take this production. And gamma is again not a problem because it's not related with the alpha. Does it make sense what I'm saying? Okay, so we have to left factor it. So how we do that? So what we do is we say here like this, we say A goes to, then we say take up these prefixes, what are the prefixes we have, take up them as a common, alpha as a common. Okay, and beta 1, whatever the after that it is, call that as A prime. Okay, and or gamma is not a problem, we can keep it there, but this is the A prime replaces suffixes. Okay, then get that A prime here and try to place it here. Now how we place it here, because A prime is here it was beta 1, then it was beta n and so on, right? So I will say A prime as beta 1, okay, or so on up to beta n. The suffixes get it downside. So what will happen by that is, because we were not able to see after taking some token, we will say, for example, in a mood to take a decision that we should take the alpha. But should we take alpha beta 1 or alpha beta 2 or alpha beta n, that can be only seen when we have seen the alpha, and now we have seen the next choice is, say for example, beta 2, so we should take beta 2. But right now we are not in a position, we are in a position only to say that we have to choose alpha, but not what after alpha. Okay, so that means first we should take the alpha, and after that we are in a position to see after alpha which beta 1 or beta 2 we should choose. Okay, and that's what we are doing here, we are taking the alpha. Okay, and right now we are not deciding that should we go to this production or this production or whatever the production. So here we take up the alpha, and when we see the alpha, now we are in a position to see which beta to choose. So at when we try to use the production A prime, we are basically in a position to see the next token and see should we take beta 1 or beta 2 or beta n. Now we are here in a position exactly to choose out of these suffixes which suffix to choose. Okay. One more thing here, a and a primes are actually non-terminals, okay, and alphas, the betas are strings of symbols, and we should mind one thing: alpha should not be epsilon, because if it is epsilon, then we exactly know that which beta we have, okay. And gamma actually represents all alternatives for a productions that do not start with alpha, okay, that doesn't have alpha in it. Whatever it is, that means it's not giving us any confusion, so it can be there. Okay, now using the same rule, let us try to left factor this grammar. Let me write it again here in the proper way. We said that we have e gives t plus e or t. Now which is the common prefix? There may be something like a also here, which is a non-terminal, not a problem, whatever. Now what are the common prefixes? That is t. So we say first e gives to t, which is a common, and I call whatever the suffixes I have here. I don't have anything, but here I have, so I call it as a e prime, okay, and a stays there because that's the gamma, stayed there, no problem. Now e prime will come here and it sees out of this e prime it is the plus e which was left out, right? So that means we have plus e. But in case of this guy t, there's no suffix, so I have to use then the epsilon to say that there is no suffix. Does it make sense? Now here we had a confusion to choose out of the two. Now here we don't have. When we see the t, okay, we see the t only, and then we are in a position to see whether it is t plus e prime or it is only t. If it is t plus e, I will use this production, okay, plus e, or if it is t only, I will use the epsilon. Let's take up another say for example a gives you int or int plus t and something else, okay, let it be b this time, no problem. Now look at here, what is the common prefix? The common prefix is int. Now because if our look ahead says we have an int, so we should be able to decide exactly which production to use. That's the predictive parser. This is how predictive parser works. But here int is in a two production. Should we use this production or should we use this production? Is after int nothing or is after int plus something? So that will be understood only when we read the token int and try to see the next token. But right now we are in a position to see only the int. So when we see the int, okay, we are not in a position to tell which production. So what we do is we say here a, and which is the common prefix, that is the int. We keep the int, and whatever is something gamma, keep it there, not a problem. And whatever is left out, suffixes, I have to call it, say for example a prime, right? I call it a prime. Now a prime is, which we'll talk about the suffixes. In this case it is nothing, okay, and in this case it is plus t. So I will use the plus t or epsilon, okay, because in this case, because what will happen is when we read the int, we know we are on an int. After that we'll see whether there is a plus or nothing. So we will exactly in a mood to say which production to use, this production or this production. Does it make sense? Let us take up another example. Say for example we got an s gives if e then s1 if, or let me write it here, or if e then s, let it be again s, and let me call it s, then s, else s, or there's something a. Now look here, this if e then s, and if e then s, else s. So this guy has only if part, this guy has also the else part, and then there is something which is nothing to do with the if, okay, that's the gamma part. Now the common prefix is if e then s, right? Okay, so what I do is I will say here s is equal to if e then s, and whatever left out is I call it the s prime, and or a will stay there as a gamma. I don't have any problem with that. Now s prime has to talk about the suffixes, okay, and here the suffix is nothing, that is epsilon, and in this case suffix is, because if then s, this is the prefix, we are talking about it here, okay. Now s prime will talk about suffix, that's else s, so this will come here else s, and in this case there was no suffix, so for that we have an epsilon. Okay, does it make sense?